In this video, I'm planning on going over the derivation of energy balance for unsteady flow in open systems. And this is basically just a continuation of what we've been doing. So we've actually already derived the equation that we need in a previous video. I derived the general energy balance, and I derived the really general equation that applies to open systems, and it applied for steady and unsteady flow, and then we made some assumptions to it to make it so that we basically set the time derivatives to 0, so then it only applied for steady flow. And so that's what we've been solving so far. Now we want to look at unsteady flow. So unsteady flow basically means that there's changes in the control volume with time. So unsteady flow means that there's changes in the control volume with time. And by now, I think that you should have a pretty good idea of what a control volume is, but just in case, the control volume is the area of interest that we're looking at. So, for instance, if we have a diffuser, we would define the control volume like this. So then there's still fluid moving through the control volume, but we're looking at the fluid right here where it's coming in, and right here where it's going out, and then the walls of the diffuser form a natural boundary. And the reason why we need to define a control volume is because if we're going to solve the diffuser problem or nozzle or any other problem for various properties or different things of interest, we need to have a definition of where the fluid's going in and where it's going out, because if we don't, then what do we put here in our equation? What do we put here in our equation? So a control volume is really just a mathematical construct, and it's basically just what we're in, like the area that we're interested in whatever it is we're analyzing. I do want to mention that this unsteady flow is also called transient flow. So you'll see it called both things. And this unsteady flow, this could apply to a few different problems. The ones that we're going to be mostly interested in here are if you're if you're blowing up a balloon or if you're inflating a tire, that's going to be the mass inside your balloon or your tire is going to be changing with time. So we say that that's transient flow. If you're discharging something, let's say that you're letting the air out of a tire. So basically these are often called, like, since we're either going to be adding fluid to a system, so basically charging the system, or if we're going to be taking fluid out of a system, so basically discharging, these are often called charging and discharging problems. So I mean, the example of what I was just talking about, let's say that we have a tank and we're filling it up with water. So right now it doesn't have very much water in it. Let's say that we're filling it up with water, and so the water level is going to rise in the tank, and so we're going to, over time, fill up the tank with water. And the other type of problem, so these are the problems we're mainly going to be looking at, but the other type of problem you can solve with this unsteady flow is, let's say that you're in a startup or shutdown phase of one of these other systems we've been looking at. Like, let's say that we're looking at this diffuser, and so let's say that water's going through it. So when we first turn the flow for the water on, this diffuser is going to have some water, and then it's going to have some more water and some more water. So it's going to eventually fill up with water over time. But while it's filling up, the mass of the water inside the diffuser is changing with time. And eventually we know that it reaches a sort of steady state or steady flow where the mass of the water isn't changing in the diffuser with time. And the same thing happens when we shut down the diffuser. So when we shut down the diffuser, there's eventually a little bit less water, a little bit less, a little bit less. So these are the types of problems that this unsteady flow applies to. And one difference with the unsteady flow versus a steady flow is with the steady flow, we didn't have a definite start and end time. But with the unsteady flow, there's a definite start and end time. So basically there's a finite time period over which we're analyzing the problem. And we didn't have that with the steady flow processes, because if the steady flow is not changing with time, so it doesn't really matter how much time is. One thing with these unsteady flow problems is they can be really difficult to analyze, because the problem is the properties can change at the inlets and exits during the process. So for instance, let's say that we have a container that we're filling up. So we have pipe coming in, and so let's just say that we have refrigerant. So we can define the thermodynamic state of the refrigerant with temperature, pressure, the specific volume. So we've seen all of this, the state, actually the phase. So we've seen all of this already. We've been using this information to analyze problems and find other properties. So one thing with these unsteady state problems is, as the fluid is coming into the system, the properties might be changing with time. So for instance, as this fluid is coming in through this pipe, the temperature might be changing with time. And as you can imagine, that would make this problem pretty hard to analyze. So the one assumption we're going to make as we're analyzing these unsteady flow problems is we're going to assume that they are a uniform flow process. And what this means is that the fluid flow at the inlet and outlet is uniform and steady. So the fluid flow at the inlet and outlet is uniform, steady, and basically the properties don't change with time. So we're going to assume that the properties don't change with time. And if they do, we're going to take the average. So if they do, we're just going to take the average and then assume that it's a constant at the average. So for instance, if with this refrigerant flowing into this container, let's say the temperature is changing with time of the refrigerant, we're just going to take the average temperature and use one temperature. So we're not going to try and analyze this problem with the temperature changing with time, because quite frankly, that's going to make the problem a lot more complex, and you're probably going to need a numerical solver at that point to solve the problem. And what we're trying to do right now is find ways that we can simplify these problems enough to where they're solvable by hand and to where we can quickly get solutions. Because if you're working on this on the job, let's say you have this exact scenario, and let's say the temperature and pressure of your refrigerant is changing as it's flowing into the container, it might be important eventually to completely solve that problem. So you might do a numerical model that's modeling the flow, the unsteady flow of that refrigerant, and the fact that the temperature and pressure and therefore its thermodynamic state are changing with time. But it might be important to be able to get a rough estimate of what's going on in the system before you go through and spend a lot of time building a numerical model to solve a problem. And so that's what we're trying to do here, is we're trying to figure out ways that we can simplify a problem to where we can get quick answers and get quick ideas of what's going on in the system, and then later on you might do the more involved numerical model to solve the problem. So, but you do want to recognize that we're making this assumption, and so that's going to apply to the equations that we're using here to solve these unsteady flow problems. So first of all, we're going to need both, in order to solve these problems, like the steady flow problems, we need both a mass balance and an energy balance. So we would need both the mass balance and the first law. So the mass balance is simply the mass flow rate in, so this is a sum of all of the inlets, this is assuming we have multiple inlets, minus the mass flow in, so this is going to be a sum of, all of the mass flow out, so this is going to be a sum of all of the mass out, and this is equal to the change in the mass in the control volume with time. And remember, so with the steady flow, we assume that this time derivative was 0 because the mass wasn't changing with time in the control volume. Well, now we can't assume that because the mass is changing with time in the control volume. And what we can do is we can integrate this over time, and if we do that, we get that the mass in minus the sum of the mass out is equal to the basically M2 minus M1 in the control volume. And so I want to make a distinction here because this is with the steady flow problems, we've been quite often assuming that the inlet is 1 and the outlet is 2. Well, what we don't want to do is confuse that 1 and 2 for the inlet and outlet with thermodynamic states. So now that we're doing these unsteady flow problems, we need to distinguish the mass flow in and out and the thermodynamic states. So this in and out represent the mass flow in and out, and then this 1 and 2 represent the thermodynamic states. And so what's meant by that is, let's say that at state 1 we have this amount in our container, and then at state 2 we have this amount. So this 1 and 2 isn't referring to the mass flow into or out of the container. It's referring to how much mass is in the container, like how much is there at state 1 and how much is there at state 2. So we want to make sure that we make that distinction with these problems. It wasn't as important to make it with the steady flow problems, but now we need to make it, otherwise the problems are going to get pretty confusing. Okay, so now let's look at the general form of the first law. And this was previously derived in the video on the general first law energy balance for open system problems. So what we had derived, and I'm just going to write down the equation that we had derived, and then we're going to look at how we can use it practically to solve some problems. And then and this is the mass in, and then we have the enthalpy in, plus the kinetic energy in, plus the potential energy in, is equal to the change in energy in the system with time. And remember, we assume this term was 0 for the steady flow problem, but this isn't 0 anymore because the energy in the system is going to be changing with time. And then we have plus, and then this is the sum of the outlets, so m dot out, the enthalpy out, plus the kinetic energy out squared, plus the potential energy out, plus the work. So this is the equation that we had previously derived, And so now what we want to do is figure out, okay, we want to use this equation to solve some unsteady flow problems. So we want to make it so it's a little more user friendly. So the first thing we want to do is figure out, okay, what's this term? So this term, well, we know that the energy is equal to the mass multiplied by the internal energy. So we know that the total energy, remember this E is total energy, we know that this is equal to the mass plus the internal energy multiplied by the kinetic energy plus the potential energy. So this is the internal energy, and then this is KE and PE. So we already know that. So what we can do is we can just differentiate this with time, because that's what we have here. So dE dt is equal to d dt m u plus v2 squared plus gz. Alright, so what we can do then is take this and plug it into this equation for that term. We don't need to, I don't think we need to write anything out at this point for any of these other terms. So what I want to do now is integrate this first law equation, so this one, with time. And so what I'm going to do is just go through all of the terms in this equation and integrate them with time. So first of all, we have q dot, and remember this is just dq dt. And so if we integrate this, so dq is equal to q dot dt, which is just equal to q. And so this is the first term. So what we're going to do is just go through each term in this equation and do the same thing. So we can basically integrate this entire equation. And so also remember, since we're assuming uniform flow, remember uniform flow isn't steady flow. Uniform flow is just assuming that there's no change with time in the inlet and outlet fluid properties. So basically there's no change in enthalpy, velocity, height, temperature, pressure, etc. of the fluid inlets and outlets. And so basically the only term that's going to change is the mass flow rate. So the only term that can change is m dot. dm dt, well, m dot is equal to dm dt, and we have m dot in this equation right here. So this is just equal to, so dm is equal to m dot dt. This is just equal to m. And then we have this term that we came up with for the change in energy, or the change in total energy with time. So if we integrate that, we have dE dt, and this was equal to d dt u plus v2 squared plus gz. This is just going to be equal to, so, and remember with this m2 and m1, this is going to be referring to state 1 and state 2, not the inlet and outlet. So we have m2 multiplied by u2 v2 squared plus gz2 minus m1 u1 plus v1 squared over 2 plus gz1. And I just want to be really clear, because this can be confusing. These refer to state 1 and 2, not the inlet and outlets. So now what we can do is we can just combine everything. I didn't do the work term, like if we go back up to this equation, the work is just going to be like Q. We're just going to get work and I'll just do it. So we have dW dt is equal to the work. And so if we integrate this, dW is equal to the work dt, so this is just equal to W. And this m dot out is, or this out term is going to be the same as the in term with different subscripts. So we have everything that we can go ahead and write this equation. So I'm going to combine, and we get the Q plus, and I'm going to move the work over just so that this is in a more standard form. So Q minus W, I'm going to put the inlet term on this side and then the outlet term on the other side. So we have in, and this is the mass in, and we have the enthalpy in plus the kinetic energy, and this is in plus G Z in, and then this is equal to M2. So remember, this is our dE dt term. So U2 plus V2 squared over 2 plus G Z2 minus M1 U1 plus V1 squared over 2 plus G Z1, and then this is all plus our outlet term. So this is the outlet, the sum of the outlets, so H out plus V out squared over 2 plus G Z out. And then I already moved the work term over to the other side. So this is our equation. And so this is basically the first law for uniform flow. So this is the energy balance for uniform flow. And I want to point out a few things in here. First of all, we have the Q, like the other energy balances we've done, we have Q and W. But then this has kind of a combination of both the open and closed flow systems. So we have terms with enthalpy, and so that would be like this term and this term. So these relate to the microscopic energies of the flowing fluid. And this makes sense because they have enthalpy, and remember the enthalpy includes the PV work, and when we have a flowing fluid we have PV work in order to push the fluid element into and out of the control volume. And then we also have some terms with just the internal energy, and so that's these terms. And so what these terms represent, these are I'm just going to do this, these are the microscopic energies of non-flowing fluids. So this is the fluid that's in the container and it's non-flowing. So now we have this giant equation. What we want to do now is look at a couple special cases of this equation. So first of all, we want to, so I'm just going to put special cases. So this equation is very general. This equation has multiple inlets and outlets. The only thing that this equation doesn't allow for is changing conditions at the inlets and outlets, and that's because we assumed this uniform flow. But other than that, this equation is pretty general. So let's look at some special cases. The first one is we want to assume that there's only one inlet and one outlet. And the other thing we want to do is we want to assume that the change in kinetic and potential energies are zero. So we're going to assume that delta KE is zero and delta PE is 0. So the change in potential energy being 0 kind of makes sense, because if we just have a container that we're filling up, it makes sense that there's not going to be a change in potential energy unless it's like a giant container that's several meters high or something. But we're assuming that the change in potential energy is 0. The change in kinetic energy is a little bit more, so that we're going to assume it's 0 just to develop these equations, but you might have times when you need to consider it. But in general, we're going to consider that the speeds, like if we're filling a container or if we're removing fluid from a container, we're going to assume that the speeds are low. So we're going to assume slow velocities. And so we're going to assume these slow velocities when we're filling or emptying a container. So if we have slow velocities, we can assume that the change in kinetic energy is approximately 0. And that's probably going to actually be a pretty good assumption, because the change in enthalpy and the internal energies are probably going to be quite a bit bigger than the change in velocity, unless you have like fluid that's coming into your container at Mach speed and then it's suddenly stopping. But with this said, there might be some times where you need to consider the kinetic energy term. And then if that's the case, you just wouldn't use these special cases. You would go back to this equation and cross out all of the terms that you're assuming are 0 and leave the kinetic energy in your equation. But we're going to be taking it out. So if we look at the one inlet, one outlet, let's consider filling a tank first. So we're filling a tank and we're assuming a single, well, basically if we're filling a tank, we don't have an exit stream, we only have an inlet stream. So we have one inlet stream. And this makes sense because if we're filling a tank, we don't want fluid flowing out. We want to, so there's one inlet stream. And what this equation ends up being, once we go up here, if we're filling a tank and we're assuming that the change in kinetic and potential energies are 0, we're going to, first of all, lose, and I don't want to cross anything out in this equation, so I'll just do this. We're going to lose all of our outlet terms because there's no outlet. We're also going to lose all of the kinetic and potential energy terms in these equations for the non-flowing fluid. And so we have the inlet, but the inlet loses all of the potential and kinetic energy terms. So basically what we're left with is Q minus W is equal to negative mass in. So go back up here. So I'm also moving this mass in over to the other side. So now it's negative multiplied by the enthalpy in plus, and then we have our non-flowing fluid terms. So M2 U2 minus M1 U1. So this is the first law when you're filling a tank. And this is also called charging. And with this equation, you're still going to need to solve the mass balance equation. So the mass balance equation is just going to become this. So if we go back up here to the mass balance, we have M in minus M out is equal to the change in the mass in the control volume with time. So we're just going to have, since we just have mass in, we're just going to have the mass in is equal to M2 minus M1. And remember, these are the states. So these 1s and 2s don't refer to inlets and outlets. All right, now let's look at the same thing. So the special case, and this time we want to look at emptying a tank. So emptying a tank, and this is also called discharging a tank. So if we go back up here and look at our equation, we know that, so for emptying the tank, we don't have any flow in, so this term becomes 0. And so we have our mass out term, but we're getting rid of all of the kinetic and potential energy terms, and then we still have this part of the equation, but we're getting rid of the kinetic and potential energy terms in that as well. So we basically end up with Q minus W is equal to M2 U2 minus M1 U1 plus the mass out multiplied by the enthalpy out. And so this is our first law equation for filling a tank, or sorry, discharging a tank. So first law for emptying a tank. And then our mass balance is going to be so it's going to be minus mass out is equal to M2 minus M1. So we can just multiply through this negative sign and we get M out is equal to M1 minus M2. Alright, so now what I want to do is, in the next video, I'm going to go through an example problem of how you would apply these equations to solve an unsteady flow problem.